analysing single samples of data, and then we're going to talk about what can we do when we have got two potential kind of like groups of people and we want to do a comparison as to whether one group of people or objects have a failure time that's longer or shorter than another group of objects. Okay, but we're going to start off still by kind of just thinking about one group and trying to model one particular kind of group. So here we have an example of 10 patients who have presented at hospital with quite an advanced stage of lung cancer. And these people have kind of been put into some particular kind of like treatment, and they have been studied either until the study has ended, which was 90 days after it started, or until they sadly died. Okay, so each patient entered the trial, the whole trial lasted 90 days. Each patient entered the trial at a different time, and so how long I could potentially observe them for was slightly different for each patient. So this patient entered on 18 days. My whole study only lasted 90, so I could have only had a maximum time that I observed them for 72. Okay, so most patients did kind of sadly die in that particular period, but there were 3 patients who were still alive when the study finished. So we know that this patient here died 2 days after they came to the hospital. This patient died 51 days after they came to the hospital. This patient here, all I know is that they were still alive after 72 days. Okay, so that's the data like that. And what we're going to try and do is we're going to try and find out about the underlying failure time distribution when we have sort of censoring as we do here. Okay, so the first thing we should always do, this is horrible chalk, is plot a Kaplan-Meier estimate. Okay, so we might plot a Kaplan-Meier estimate. And that's first I'm going to do because at the moment we don't know if we can plausibly model my failure times by any particular distribution. So I'm going to plot my Kaplan-Meier estimate and maybe I get something that looks like that. Okay, I would look at that and I would kind of go, well, does that look like any of the... So this is my estimate of my survivor function. And I would say, well, does that look like a particular kind of like standard distribution? And in this case, maybe I might think it looks like what I would get if t was... followed a exponential distribution. Okay, so it looks roughly kind of like exponential decay. So we might model my failure times as coming from an exponential distribution with rate lambda. Okay, so if we've decided, well, that looks reasonably exponentially distributed, we might now switch to deciding, well, we can do a parametric analysis now. So we can try and estimate what lambda is based upon my data and knowing the fact that I have some censored observations. And last time we worked out that when we have censored observations, if I want to get an estimate of lambda hat, we just use my modified MLE. So exactly the same idea of maximum likelihood, but take into account that we've got some censorings, and we get an estimate for lambda hat, which is the sum of the delta i's divided by the sum of the delta I ti plus 1 minus delta I ci. Okay, that looks a bit complicated. In reality, all it is working out in my entire study how many people failed and dividing it by the total time that I observe people alive. Okay, so this is the total time that all of the people who failed were observed alive, and this bit here is the censored people, how long I observed those censored people alive before I lost contact with them. Okay, so that's all we're going to kind of do here. We're going to work out, well, how many people actually did we observe to fail, and what was the total length of time that we observed everybody being alive. So the number of people who observed to fail are this individual, that one, that one, that one, that one, and that one. So that is 7 individuals are observed to fail. Of those people who are observed to fail, how long did we observe them for? So 2 plus 51 plus 33 plus 27 plus 14 plus 24 plus 4. And for the individuals who were censored, so the individuals who have zeros in their delta i's, how long did we observe them for? Well, 72 plus 60 plus 21. Okay. So that's what I've got on this particular kind of slide here. So we observed 7 deaths during the study. Of the people who died, we observed those people for 155 days. And for the people who were censored, we observed those people for 153 days until they were censored and we don't know what happened to them. Okay, so if I want to work, if I'm going to fit a exponential distribution to my data, all I have to do is divide 7 by the total length of time that I observed everybody alive for, which is 308, and I get 0.0227. Okay, so that's my MLE for my rate parameter if I'm happy modelling my data by an exponential distribution. So lambda's a rate. If I want to work out the mean lifetime, then I can just work out 1 over lambda. So the expected value of an exponential is 1 over the rate. Because my MLE works by, it's invariant, I can just plug in my lambda hat. If I get put 1 over 0.0227, I get that I think people, their expected lifetime after they'd presented at my hospital would be 44 days. Okay, if we want to work out an estimate for the variance of lambda hat, I can use the approximate formula that I gave you last time. You work out lambda hat divided by the total number of people who failed. So lambda hat squared, in this case, divided by 7. Get this. And if I want to work out a 95% confidence interval for lambda, I use my standard formula for a 95% confidence interval. Okay, if I wanted to work out then a 95% confidence for the mean lifetime, I could work out 1 over this and 1 over that, and that will give me an interval as well. Or I could use what I talked about last time about how you estimate the variance of a function of lambda. Okay. Does anyone have any questions about that? No? Great. Okay. Again, you'll be glad to know you don't actually generally have to kind of do this in practice, and you don't just have to restrict yourself to an exponential distribution. The survival library in R will allow you to fit a whole load of different random variables to your data and work out the MLE in the presence of censoring. So you can choose a viable, an exponential, a logistic, a log normal, a log logistic, lots and lots. And the function that you can do that in is called servreg. Exactly what servreg gives you as output, you need to kind of know how that relates to the particular kind of parameter. So I don't want to talk about it too much here because servreg is actually used later on in the course. I just want to say in the case of when you're fitting an exponential model, then it gives you a term called intercept, and lambda is 1 over e to the intercept. Okay, but you'll see later on in the course why it does that, because servreg is a slightly more powerful function than just allowing you to fit an MLE to one group of data. And as I said, if we want to find out a confidence interval for a particular parameter, the easiest thing to do is R will give you an intercept and a standard error. Take that intercept, add or subtract whatever times the standard error that you want to work out, so plus or minus 1.96 times the standard error, and then do that transformation to the two values that you get for the intercept. We'll see that in a second. Okay, and then just convert that. Okay, so I've got an example of how you actually kind of like do that now. Okay, so here's my lung cancer data. Okay, so here's my lung cancer data. That if the censoring is 1, that means somebody's observed to fail. If the censoring variable is 0, that means we just know that somebody lasted longer than that particular time. Okay, so that's a summary of the data that was in that table. If I add up the number of deaths, that's just adding up the censor variable, so that's 7. If I add up the time here, then because this column is a time that I've observed everybody alive, this is basically just my denominator in my thing that I work out here. Okay, so 7 over 308. Okay, if I want to do it in R, rather than work it out by hand, or if I want to choose a more complicated distribution than just an exponential, first thing I need to do is I need to create this survival object by telling R to link together the times and the censoring variable, and that the censoring is right censoring. So I'm going to do that. Okay, then I'm going to do my first thing that I should always do is try and plot a Kaplan-Meier estimate. So that's with the servfit command. And we get this plot here. Okay, which hopefully looks a little bit like that one on the screen. Okay, so it's reasonably plausible that that shows something that looks a little bit like exponential decay. So I might plot that and I might kind of think, well, that looks reasonably like the Kaplan-Meier estimate I would get if my survival time is exponentially distributed. So let's proceed by modelling my survival times with an exponential distribution and see what we get. So now I'm going to switch to a parametric approach, having done that first step, and then get R to work out what my MLE estimate is. Okay, and that's using this servreg command. You put in on the left-hand side your survival object, and then you put just tilde1, and you tell it what distribution you want it to fit. Okay, and then this gives you some output. So in particular, it will give you an intercept term, which is related for the exponential to the rate by if I take 1 over e to the power intercept. That's my lambda parameter. And it tells me kind of like some other things as well. Basically, it works out the MLE by doing some iterations. Okay, but we get a value of the intercept of 3.784 and a standard error of 0.378. Okay, so they're the important things to get from that. And from that, we can go back to getting an estimate for lambda. Okay, so summarise Kaplan-Meier plot first. Have a look as to whether that looks like a particular distribution that you're happy to proceed with modelling. If it does, great. Maybe switch to a parametric approach. If it doesn't, then you're going to need to stay with a non-parametric approach. This looks reasonably like exponential decay, so I'm going to try and model my data with t being exponential with rate lambda. I did that with my servreg command, and that gave me an intercept value of 3.78 and a standard error of 0.378. So if I want to work out an estimate of lambda, I work out 1 over e to the intercept. So that's 1 over e to the 3.78, which is 0.0228, which is basically the same as what we worked out when we did it by hand. And if I want to work out a confidence interval, and as I said, it's easiest to work out a confidence interval for the intercept. So take 3.78 plus or minus 1.96 times its standard error. That'll give you two numbers. And then work out 1 over e of both of those numbers separately, and that'll give you an interval. So in this case, we get an interval of 0.01 up to 0.05 for what it thinks is a potential confidence interval for lambda. It's a bit different from what we got when we worked out by hand, but with such a small sample size, they're basically very rough approximations anyway, so they're not probably that useful when you've only got 8 patients. Okay. So, any questions? Yeah.
In the Kaplan-Meier estimates, what are the other distributions we likely fit in?
So, where's the? Is it in this? Oh. Hang on. Oh, not that one. Okay, so there's loads. So you're quite free as to choose what you think the distribution of your failure times are. So obviously you need your failure times to always be something that's positive. Okay, so exponential kind of has the fact that if you have an exponential random variable, it'll always be positive. If you have a variable, it'll always be positive. If you have a log normal, that will also always be positive. So they're kind of 3 standard ones that people use. But there are other ones as well. I'm not exact. I think R probably has like 7 or 8 that you can sort of choose between. To try and choose between them, you either need to kind of have some exterior knowledge as to what you think the failure times actually are. So you might speak to a doctor or speak to somebody in an engineering firm, and they might say, I think this is a Weibull distribution, in which case you might fit a Weibull. Or alternatively, as I said, try plotting the Kaplan-Meier, and then each distribution that you might choose to model will have a survival function. So if you think t might be exponential lambda, then the survivor function for an exponential random variable looks like e to the minus lambda t. So you'd plot your Kaplan-Meier estimate, and you'd go, does that look a bit like e to the minus lambda t for some lambda? I might choose, therefore, to model with an exponential distribution. For a Weibull, it's a bit more complicated to kind of like identify, but if you were going to model something with a Weibull distribution and you plotted the Kaplan-Meier estimate, it would look more like this. So as I said, it's not that different from here. It still kind of like has some exponential decay, but it's a slightly different power of t. So yeah, there's no perfect answer as to deciding if you're going to choose parametric which particular kind of like distribution you want to go for. but there are lots that you can choose between. Okay. So that's everything that that I'm going to cover that we might want to do with single samples. So summary is single sample data. First thing you should do is always plot either a life table or a Kaplan-Meier estimate. And then based on that, you should try and think about, do I need to proceed with a non-parametric analysis, or can I do a parametric analysis? So you plot your Kaplan-Meier estimates. You would go, does that look like a particular distribution that I'm reasonably happy with? Modeling my data by, if it is, you might switch to a parametric approach. If it's not, you're going to need to stick with a non-parametric approach. And then if you're going to go for parametric, you can still do maximum likelihood to work out your parameters which entirely specify your distribution. Okay, so that's one sample of data. It's not massively interesting if we've only probably got one sample of data. Predominantly what we're going to be interested in is trying to compare two different samples. So people that I have come into my hospital, I've given them maybe two different treatments. I want to know if there's a difference between whether I've given them treatment A or treatment B, or if you're in an engineering firm, you've got two different ways of kind of making a particular widget, and you want to kind of know, if I make my widget with method A, is that going to last longer than if I make my widget with method B? Okay, so that's what we're going to talk about in the next chapter, how we can try and compare data where we think they come from two separate groups. Okay, and just like last time, or just like the last chapter, how we can do this will depend upon whether we think we can do a parametric approach, or we're going to stick with a non-parametric approach. So still, the first thing you should always do is plot Kaplan-Meier estimates for each group. And that should hopefully help you to decide, can I take a parametric approach? Do both of these Kaplan-Meier plots look exponential or like the survivor function of something I'm happy with? In which case, we might go parametric. If they don't, then I'm going to need to stick with a non-parametric approach to do the comparison between the two. If we're going to go for non-parametric, then the method that we're going to apply is called a log rank test to have a statistical way of comparing the two groups. If we're going for a parametric approach, then we're still going to use kind of likelihood, and we've got two options. We can either do a likelihood ratio test or a maximum likelihood test. So I'm going to start off with the non-parametric version. Okay, and I'm going to consider some sample data. So this is some sample data on 12 patients who have come into a hospital with a brain tumour, and they're coming to my hospital, and I have randomised them to one of two treatment groups. So group 1 have just received radiation therapy for their brain tumour, and group 2 have received radiation therapy and chemotherapy. And then I've observed people for a year after the start of my study, and I've noted down either when people died or when I lost contact with them when they were still alive. Okay, so in my radiation therapy group, somebody died after 10 weeks, somebody died after 26 weeks, 28, 30, 41, and then this individual I lost contact with after 12 weeks when they were still alive. Okay, and then radiation therapy and chemotherapy, slightly different. Okay, and my question is going to be, is it better to give somebody radiation therapy and chemotherapy rather than just radiation therapy? So basically, are the survival times in group 2 statistically significantly different from group 1. Okay, so here a star means they're a censored observation. Okay, so first thing we're going to do is we're going to plot some Kaplan-Meier estimates. Okay, so here are Kaplan-Meier estimates for the two groups separately. The red dashed line is the radiation therapy, and the blue dotted line is the people who've got radiation and chemotherapy. So it looks here, bearing in mind this here is an axis, the probability to survive longer than a particular time, so it's good to be high. So maybe 40 weeks. If you're low, the probability of surviving at least 40 weeks is low. If you're high up here, the probability of surviving at least 40 weeks is high. Okay, so basically we'd like to be in the upper bit of the plot. So based on that, it looks as though potentially radiation and chemotherapy means that you will survive longer than just if you give somebody radiation therapy. Okay, but we'd like to be able to kind of like test that statistically significantly. So we've got some plots. They kind of maybe give you a rough idea, but how can we kind of formally decide whether the difference between those two plots is statistically significant or not? So what we're going to try and do is we're going to try and formalize that question into our standard statistics idea, which is a hypothesis test. So a hypothesis test all hypothesis tests have 3 steps. So the first step is write down what my null and my alternative hypothesis is. My second step is try and come up with a test statistic that is going to help me distinguish between my null and my alternative. And step 3 is, step 2, and then step 2 is work out a test statistic and then take your observed data and work out an observed value of that test statistic. And then step 3 is kind of saying, well, under my null hypothesis, what values of that test statistic might I get? How extreme is what I've observed compared with what I might get under my null hypothesis? Okay, so we're going to still do those particular kind of things. So null and alternative are quite easy to kind of like write down. So my null hypothesis is that basically there's no difference between the two groups. So they're both modeled by the same underlying random variable. So the survivor function of group 1 is equal to the survivor function of group 2. So that's my null hypothesis. Okay, and we're going to stick to that unless we kind of have some evidence against it. My alternative hypothesis is that the distributions of group 1 and group 2 are different. And so I can write that down that says for at least some value t, the survivor function in group 1 at time t is not equal to the survivor function in group 2 at time t. Okay, so my null is basically, they're all modeled by the same random variable. My alternative is there's a difference between the two random variables, so there's a difference between the two survivor functions. Okay, so that's my null and my alternative. Now I need to do step 2 and step 3. So step 2 is try and find a test statistic that's going to help me distinguish between those. And then step 3 is find out what the distribution of that test statistic is under my null hypothesis. And if we're going non-parametric, then we're going to implement something called a log rank test. And what we're going to try and do is we're going to try and work out if the null hypothesis were true, so basically there's no difference between the two groups, how many deaths would I expect to see in group 1 and group 2? And then I'm going to compare that with my actual observed number of deaths in group 1 and group 2. And then if they're very different, so what I observe is very different than what I would expect under the null hypothesis, that's going to give me evidence to reject my null hypothesis. Okay, so I've got a sort of picture of trying to explain that. So under my log rank test, then if I assume for the moment that my null hypothesis is true, and then I have at some particular time in group A, I have some people, and in group 2 I also have some people who are still in my study. Okay, so at some particular time in my study, in group 1 maybe I've got 3 people who are in my study, and group 2 I have 4 people who are still alive in my study. Okay, now if we know there is a death or a failure at that time, then under my null hypothesis, basically all these people are kind of the same. Okay, so under my null hypothesis, they all have the same failure time distribution. So under my null hypothesis, it's equally likely that any one of those 7 people could have been the person who failed. Okay, so I can work out, given there's a death or a failure at that particular time, what's the expected number of people who would have failed in group 1, and what's the expected number of people who will have failed in group 2. So I've got given a single death at time T1, then the expected number of deaths in group 1 is equally likely to be any of those 7 people. The probability that that death lies in group 1 is 3/7. So the expected number of deaths in group 1 is 3/7. And the expected number of deaths in group 2 is 4/7. Okay, so basically I've got to split up the death that I have observed between the 2 groups, equally likely to be any of the 7 people. So the probability that death lies in here is 3/7. I've got 1 death, so the expected number of deaths is 3/7 in this group. Here I've got 4 out of my 7 people, so the probability that the death lies in this group is 4/7, so the expected number of deaths in group 2 is 4/7. Okay, so that's true under my null hypothesis. And I can do that for basically every single time that I observe some deaths. I can say, well, under my null hypothesis, where there's no difference between anybody, where would I expect the deaths to fall? Okay, and then if I observe some data where actually all of the deaths keep falling in group 1 or group 2, so they're very different from the expected numbers, then that's going to give me some evidence against my null hypothesis, and it's going to say, well, actually, all the deaths seem to fall in group 1 rather than group 2, so therefore it's not very likely that the null hypothesis is true, that there's no difference between these 2 groups. Okay, does that make sense as an idea of how to, well, does this make sense as how you work out the expected value, and then the idea of how you compare these with the actual observed numbers that you get? Good. So let's try and do that for this brain tumour. example. Okay, so that's basically what I've this is what I've kind of described here. But hopefully, maybe this makes a bit more sense. But we can go through it as a particular example. So let's go back to our actual sort of raw data, and let's try and work out how we can do a log rank test for this particular set of data. So the first thing that I would always recommend you do, if you have data like that, is just try and like order the times in each particular group, because it makes it a lot easier. Okay, so I have two groups. Okay, and in group one, the first time something happened at all was after 10 weeks, and then I observed somebody fail. The second time anything happened was at 12 weeks, and that was a censoring. So all I know is that somebody hadn't died by 12 weeks, but I don't know exactly when they died after that. Then I've got 26 weeks, and then I've got 28 weeks, and then I've got 30 weeks, and then I've got 41 weeks. Okay, so just slightly order them so they're all in ascending order. Group 2, my radiation and chemotherapy. First time anything happened was at 15 weeks. Then I have 24 weeks. And I have 30. And then 32. What have I written down? 42. Sorry. So 40. And they were censored. And then there's a 42 and they failed, and a 42 that was censored. Okay, and then we're going to try and apply this idea. I should do that here. Okay, so we're going to create a table based upon that, which lists the failure events, their times, the number of people who are at risk in each group. So the number of people who could have failed, who were still under study and hadn't failed yet. In group 1, the number of people in group 2, the number of people in total, then the number of deaths in group 1, in group 2, and in total, and then the expected number of deaths under my null hypothesis in group 1 and group 2. Okay, so if I look at my actual failure times, the first time anyone failed was 10 weeks. The second failure that I saw was at 24. The third failure was 26. The fourth failure, 28. And then 30. And then 41. And then 42. 1, 2, 3, 4, 5, 6, 7. Okay, so just before time 10 weeks, how many people was I still looking at in group 1? Yeah. And how many people was I still looking at in group 2? Okay, how many deaths at 10 weeks did I see in group 1? How many in group 2? Okay, so now 24 weeks, how many people was I still studying in group 1?
4.
Yeah. Okay, so this person had already died and I'd lost contact with that person. So I basically have that person, that person, that person, and that person who's still in my study. How many in group 2? 5. Yeah. Okay. And then how many deaths in group 1 at 24 weeks did I actually observe? Okay. How many in group 2? So 1 in total. Okay. So now 26 weeks. How many people are in group 1? And then 8. And then death like that. And then 3, 4, 7. 1, 2, 4, 6. And here at 30 weeks, I saw both a death in group 1 and a death in group 2. Okay, and then a 1, 3, 4. 1, 0, 1, and then okay, so in total I saw 5 deaths in group 1 and I saw 3 deaths in group 2. Okay, so now I'm going to try and compare that with my expected number under my null hypothesis. Okay, so at time 10, I had 1 death that I need to split up evenly between any of these 12 people. Okay, so what's the expected number of deaths in group 1?
3/7.
I don't have 3 and 4 people anymore, I'm sorry. I've got 6 in group 1 and 6 in group 2. A half, yeah. Okay, so I've got 12 people. It's equally likely to be any of those people that have failed. So the expected number of deaths in group 1 is going to be 6/12 times 1. Expected number of deaths in group 2 is going to be 6/12 times 1. Okay, so now at 24, I've got 1 death. I've got 9 people to split it up between, 4 of which in group 1 and 5 of which in group 2. So how many expected deaths are going to be in group 1?
4/9.
Yeah, and 5/9. Okay, then I've got 1 to split up between 8. And then I've got 1 to split up between 7, according to that. Okay, and then this one here, I've got 2 deaths that I need to split up between 6. So how many do I think are going to be in group 1? Okay, so basically 2 times 2 6. Okay, because I need to split up my 2 deaths now. So I have 2 out of my 6 people are going to fail. So the probability of people failing in this group is 2/6. I've got 2 deaths to split up, and then similarly I've got 2 deaths to split up between the other group. So then I've got 1/4 and 3/4. And then I've got 0 and 1. Okay, so I can work out my expected number under my null hypothesis, and I get E1, which is 2.87. So if my null hypothesis were correct, I would have expected the number of deaths in group 1 to be 2.87 and the number of deaths in group 2 to be 5.13. Okay, so now what I'm going to use as my test statistic is I'm going to compare these numbers with these numbers and see how different they are. Okay, and what we're going to do is basically use a chi-squared test. So you've seen chi-squared tests before. You work out observed numbers and expected numbers. You square the difference between kind of different boxes and you divide by the expected number. So we're going to do exactly the same here. So for group 1, we're going to look at the squared difference between what I observed and expected and divide it by the number expected. And then I'm going to add to it exactly the same for the second group. And then under my null hypothesis, this should approximately follow a chi-squared distribution with 1 degree of freedom. So I can work that out and I can compare it with a chi-squared and that will tell me how extreme my test statistic was and whether I can reject my null hypothesis or I don't have enough evidence to reject my null hypothesis. So I'll work that out here. If I work out this minus that squared, divide that, plus 3 minus 5.13 squared divided by 5.13, I get a log rank test statistic of 2.46, which I can compare with a chi-squared distribution with 1 degree of freedom, and that is below the 95th quantile of that distribution. So the p-value for my data that I've observed is bigger than 0.05. So therefore I don't have that strong, I don't have very strong, I don't have, what do I want to say? I don't have significant evidence to reject the null hypothesis that the two distributions are actually the same at that 5% level.